have in the tape industry the capacity equation pretty well in hand. So this chart comes from INSIC, the Information Storage Industry Consortium. It's published every couple of years, and it's one of the greatest future-looking technology projections that we have. It holds pretty good. We use their areal density charts all the time in this industry, and the line I want you to focus on is the second line there called total data rate. The data rate for tape is increasing at 22.5% per year. That's staggering. Remember that the disk industry is not improving in performance. So tape's got this data rate game in hand. It's already the fastest data throughput technology in the industry, and now we're going to come along and see a roadmap like this for the next 8 to 10 years that's going to show incredible data rates going forward. But is that enough to go with that? This projection shows by 2025 that tape would have a 5 times native data transfer rate increase over a disk drive. And one of the concepts that's gaining a little momentum here lately, and you're going to hear from this from Quinn Mitchell at Oak Ridge, is going to be the concept of RAIT. This is like RAID for disk, except it's for tape. This is for large files that need massive amounts of throughput. This is great in a disaster recovery scenario where I need to move my whole data center electronically somewhere fast, because this multiplies the data rate. And what we do, we stripe parity around the drives in the RAIT stripe, and the parity is striped around. In this example, you can see the blocks are striped too, so instead of using one cartridge with all the records sequentially on it, we're going to do record 1 on one tape, record 2 on another, record 3, record 4. This example uses 4 tape drives in the RAIT stripe to do that with rotating parity across that. Technically, for the RAID disk equivalent, that is RAID 5, single level parity, rotating parity with that. There's also RAIT with no parity. So if you don't want to have any recovery capability, because parity gives you the ability to recover if one of those tapes or drives fails, you can stripe like this and run the risk, but you get double the throughput in this case. In fact, it's simultaneous recording of data, writing data with parity. The effective transfer rate is actually the number of drives in the RAIT group divided by the transfer rate in that group. So n-1, if you have 4 drives, for example, it'll be 3 times the transfer rate. And that's what your effective rate is. In fact, we had the great privilege to use one of Rich's engineers at Fujifilm to do some serious tests for us, complete battery of tests to verify what happens with tape performance in this case. And that proof of concept came out like this. He used the predominant open source software product, Amanda, to write data to verify what happened on that. And this is the time it took to back up about a 19 gigabyte file to write it off to tape. The initial spike you see up, if you can read that up to 240 megabytes per second, is the actual host communicating with the drive buffer, DRAM, and therefore then the rest of that time coming across is the steady time to move the data. And it runs exactly as would be advertised in a RAIT stripe at 160 megabytes per second. There are no glitches here. If you have different types of tape drives in a RAIT group, the RAIT array will run at the speed of the slowest drive. If you have different types in the RAIT group, it'll run at the capacity of the lowest drive. So you'd like to have them all equal if at all possible.